Hi, my name is Danielle, and today I'll be explaining the direct comparison test. The direct comparison test is used to find the convergence or divergence of a series. In order to do the direct comparison test, there are certain requirements that must be met. When you do the direct comparison test, you are technically comparing the series that you were given to a simpler series that you already know the convergence of. So in order to do this, there are certain requirements, and I will list them now. Number 1, it must be a positive function. So, A7. Also, for converging series, the function that you pick must be greater than the original function. So, if this is met, then if the integral of n equals infinity of b sub n converges, then the integral of n equals 0 over infinity of a sub n also converges. Second requirement is for diverging series. Also positive, but in this case, b sub n has to be less than the original function. If this is met, then if the integral is n equals 0 of b sub n diverges, then the integral also diverges. So one way to keep this straight is converging have to be bigger and diverging have to be smaller. Keep that in mind. It's pretty easy to do the direct comparison test. However, if these requirements are not met, you will have to use another test in order to solve your problem. Most times you can resort to the limit comparison test. So I will do an example of both the converging and diverging series that has been found using the direct comparison test. Example number 1 would be the integral as n is to infinity of 1 over minus 1. So, first off, you want to identify what a sub n is and b sub n is. Your a sub n in this case is 1 over n. I'm going to write n to the 1/2 minus 1. So when I write b sub n is equal to 1 over the n 1/2. We know that this here is a p series. And p is equal to 1/2, which is less than 1, so the series diverges. So, since the series we're comparing to diverges, that means that a sub n has to be bigger than b sub n. So what we'll do is we'll write 1 over n to the 1/2, which is b sub n, has to be less than or equal to a sub n, less than or equal to 1 over n to the 1/2 minus 1. We just write this out like this. We see that this is an accurate statement. So therefore, by the direct comparison test, the integral of n equals 2 to infinity of 1 over n minus 1 diverges, because this diverges. So that is an example of the direct comparison test with a diverging series. Next, I have an example of the direct comparison test with a converging series. So, example number 2, our integral is n equals 0 to infinity 4 to the n over 5 plus 3. If we look at this function, we know that a sub n is equal to 4n 5n plus 3. If we look at this function, you have if you take out the 3, you have 4 of n over 5 of n. And this is the same as 4 over 5 to the n. And we know that this is a geometric series. R is equal to 4/5, and it is less than 1, so it converges. So we know b sub n converges. So then we have to prove that b sub n is greater than a sub n. So a sub n has to be less than or equal to b sub n. And so we do and 5n plus 3 has to be less than or equal to 4. I'm just going to separate this. I just multiply through. And so you get 4n, 5n is less than 4n times 5n plus 3. And this is a true statement, so therefore, by the direct comparison test, the integral of n equals 0 to infinity of 4n, 5n plus 3 converges. And this is how you use the direct comparison test for both a converging and diverging series. It's important to ensure that you meet all the requirements for this test in order to use the test to prove convergence or divergence. Because if any part of this fails, you are not allowed to use the direct comparison test, and you will have to look at other tests in order to determine the convergence or divergence of your function. I hope this video helped.